BigQuery solved one of the hardest problem computing had, analyzing data at Google scale. The rest of the world followed it. Everybody had distributed systems, massive data pipelines, and that's how they analyze data. Today, I have Jordan Tigani, who spent decades building BigQuery. He now argues, did we build it not really wrong, but build it wrong for non-Google scale? Every company had a big data story, but did they really have a big data problem? I'm Suresh Matthew, and this is one idea. Before we dive in, if you like the show, if you watch it, please like and subscribe on YouTube. It takes just 5 seconds. This tells me that this show is valuable. People are getting value out of these conversations. And here I get to talk to these incredible engineers and just talk shop. No marketing, no sales. It's just tech and data and ideas. Thank you. Welcome to the show, Jordan.
Thank you.
BigQuery is probably one of our favorite platforms. And as a company, we do optimize and manage BigQuery autonomously. So I'm very, very close to BigQuery. So the question is not that have you built the wrong platform, but have you built the platform which was exactly the right platform for Google, but not for the rest of the world?
I had this rant from a couple of years ago that was essentially, it's like I blame Google for, screwing everything up. Doug Cutting, the creator of Hadoop, he, published a blog post that says something about like Google is, operating 3 years into the future and sending us messages back. So there was this real sense that like, everybody is going to be like Google. And, Hadoop was super popular. Everybody was using it. It was the sort of the coolest thing at the time. It was the thing, if you were an engineer, would get you the highest salary. So everybody wanted to learn Hadoop. And people quickly saw that actually most of the stuff they were using Hadoop, this incredibly complicated, machinery, most of the things they were using that for were like, it was just like one node. It was very, very simple. And it was sort of like, it was a cool thing to do. And then turned out not to be necessary. Sort of the successor to the Google tools that were, that Hadoop was based on. The successor to that, at Google was Dremel, which was the a distributed query engine that then BigQuery then, was the productized version of. And, and I think everybody at the time was operating under the assumption that like, hey, if Google has these problems, these big data problems, they've got, billions of users and, terabytes, petabytes, exabytes of data, then surely everyone else is going to experience those same problems. And it turned out, that wasn't necessarily always the case. In fact, mostly it wasn't the case. I think it just took people a long time to realize it because the tools got good enough that it's sort of like, well, it just sort of works, and it's fine. It's I don't actually need BigQuery. I don't have big queries, but this thing works, so why not keep using it? So, it was not necessarily, if you had known where the world was going to end up, it wasn't necessarily the right thing to build, but it was also, kind of a reasonable, the world is path dependent. And sort of, if you follow the kind of the path about people making locally reasonable decisions about the future, then, maybe not a bad decision, especially because, these systems take years and years to build. And so you kind of have to pick a point in the future that say, I'm going to build to that. And if that turns out that that's the way the world looks like in the future, hey, you win, that's great. And if it's over here, then you may be left with something that is not as useful, or and then you kind of have to smush it back over to where things ended up, which might be a little bit about the path that big data actually took.
So how does this happen, right? How can a technology that's not really the right fit for me creep into my brains, my company, my teams, and I start adopting it heavily? I've seen companies adopt who use BigQuery in and out for almost anything and everything, right? How does it happen?
There's a couple ways. One is there's the expectation that people have, like, well, most people don't want to raise taxes on millionaires because, well, when I'm a millionaire, I don't want to have to pay taxes. It's like, well, when my data is really big, I want this to work. When I've got a billion users, I want to make sure that this works. So I think people are designing for a scale that they believe they may have, or they just, a little bit less dismissive way of putting it is like they just don't want to have to worry about scale, and so they say, oh, I'll just use BigQuery. There was another thing that we did though in BigQuery, which is something that I've tried to take with me. When starting MotherDuck, is one of the things that BigQuery really got right was they made it really easy to use. You just go to the API or the UI, you run a query, and it just runs, and you don't have to worry about instances and spinning things up. And yes, at scale, it starts to get very complicated, but at smaller scales, it can be super easy to use. In fact, when I was originally pitching the idea behind MotherDuck to somebody who was actually the site director at the Google Seattle office from when I started in BigQuery, and and I said to him, most people don't actually have big data. And he said, well, wait, they're using BigQuery, like BigQuery. Why would they use that if they don't have big data? And it's like, well, actually, I thought about it. It's like, well, BigQuery was actually kind of two products. One is BigQuery lets you run giant queries. And actually, the tiniest sliver of a customer is actually needed for that. The other one was Easy Query. Is we make it just easy to run your queries. And that actually was the code name for our internal alpha. The thing that we were building at MotherDuck was Easy Query. We said, hey, let's take that and let's just do a really good job of that, and not have to worry about the architectural decisions that you'd have to make if you were going to try to solve the giant query problem.
The big part of it.
Yes, exactly.
And what exactly is the cost of this mistake, right? So let's say I jumped on this bandwagon, right? And I'm spending my calories there. What is the cost?
The cost is borne on two sides. The one side is on the consumer side, and it's not that high of a cost because you're using kind of the wrong thing, but nobody built the right thing. It's as if you were kind of driving to work in a tractor, and it's like, the tractor is the right thing for certain use cases, but it's probably not the right thing to, take your kids to school. You might have to go back and forth like 3 times because, there's not enough space, and, your dog might have fallen off the back. What's the cost of that? Like, I don't know what the cost of that, but it's all these little like frustrations and all these things that are a little bit longer and like, that are just sort of harder to do. And meanwhile, the company that's selling the tractors, I'm sorry if I'm going overboard with this analogy, they spend all their energy on trying to make the tractor feel like it's not a tractor. But at the end of the day, it's still a tractor. On the other side, I think is where where it ends up being higher, because the cost on the vendor side means that, they're spending all of their innovation tokens, all of their energy trying to make the tractor, drive reasonably. And so they're not spending their time on like, helping you, get there faster, like on all the things that they would make it more, make your life easier. That's where some of the biggest problems have been felt. And, to get out of the analogy and into the concrete, like in BigQuery, we optimize for throughput, meaning being able to run the biggest queries in a reasonable amount of time. At one point, my manager said, it's okay if you add a second to every query because that doesn't matter. What matters is that the giant queries run in a reasonable amount of time. Now, that's reasonable if you're running these giant pipelines or whatever, but if you're running a dashboard and the dashboard has 16 queries and each one of those is taking an extra second, like that's pretty terrible. And so I think if you look at the problems that like the people were actually having, that the problems are, like that latency is actually is sort of the important thing versus the scale. So the vendors, they move a lot more slowly because they're kind of focusing on giant scale and these giant complicated distributed systems. And then they also just everything takes longer to do and to build. An example was like there's a common join optimization where you're joining this table against this table, and in order to know whether the values in this table are theirs or is you send across a bitmap, um, and then you can do the filtering on the other side. Now, like that's like in BigQuery, that took us like I don't know, it took 2 engineers, call it 6 months to build a relatively simple optimization because there's all sorts of things that can go wrong and all sorts of problems. And like in a single node system, in a simpler system, that's the kind of thing that could have been done in a week. And so that's a tax on everybody because it takes longer to make things better. Some things never get built, and you end up just sort of using the wrong thing.
The example that you just mentioned, right? So was the complexity induced by the scale, the massive scale of the system, or the edge cases to handle edge cases?
It was the architecture that you have to build in order to handle distributed scale. The way that Google's approach to scale was basically scale out. So instead of having bigger and bigger machines, you had simple, inexpensive machines, and you just have lots of them. And that was like I think it was a computing revolution when Google made that switch, so that instead of buying these really big, more expensive machines had to have all sorts of redundant things. They just said we're going to build the system in a way such that any machine can fail at any time, doesn't matter, and they're going to be inexpensive. BigQuery, as well as Google Search, were designed to run lots of these sort of small instances. And so on one hand, it means you can just add more instances and it's very simple. On the other hand, like the mechanism in order to sort of keep track, farm out the work, you move things from one to another, handle when one of them crashes, and then the storage system is also on the same sorts of thing, and so those all can crash. And there's all sorts of like these moving parts that when they work, they're amazing. But also like if you want it to be right, and then you're building a database, it's got to be right. Then it's hard.
If you are stateless purely, then horizontal scaling is a lot easier, but seldom you get like pure stateless machines. You will have a state and cap will become a cap, right? Cap theorem is now the biggest problem.
Yeah, and in general, yes, databases are by definition not stateless. In general, the operation was stateless, but within a query, there's lots of state. Like, so your query, you have a query, and then you fan it out, and there's all sorts of the state of everything going on. And all, and during that, because like in a BigQuery, often, queries would run over thousands of machines. And so the odds are that one of those would fail at any time approaches one, the more you get.
Absolutely. Now, I've heard you mentioning about big data and big compute, and people mix it up, and that causes another set of problems, right? So explain, please, what exactly does that mean?
It used to be that when you would buy a database, you would buy a server, and the server would have a bunch of disks in it and a handful of, and CPUs in it, and it would all run in that one disk, and you'd get a bigger one when you needed more. And then separating storage and compute, it allowed you to scale each of these independently. So you could have, in the BigQuery case, you could have lots of compute units and then lots and lots of disks. And these days, more or less all cloud data systems tend to store data at rest on, object storage, equivalent of S3 or Google Cloud Storage. And that's virtually infinite. And that, really you can store an exabyte and it will be fine. But the compute that you might need is not tied to the size of the data. And so that's the kind of the key thing from the separation of storage and compute. And so actually there's two separate axes where, there are cases where you have lots of data. Let's say logs, like I'm collecting logs for 10 years. I might have like a petabyte of log, but I might only look at the last hour of logs or the day or the last week. So the size of the data is actually not material to the size of the computation. So the other axis is sort of the size of the computation you need. So there are, highly intense, you need lots of compute for small data. And then there are cases where there's lots of data, you don't need a lot of compute. There are, some in the other quadrant that are like, I need a lot of data and the compute is also intensive. But I think one of the nice things is, I remember I was saying that when Google started, machines, they were using very inexpensive small machines. Machines are much, much bigger now. Like kind of just the basic machines that are running in Amazon and, the EC2 machines, they're hundreds of cores, terabytes of RAM. And so like there are very few workloads that don't fit in that amount of size.
Now, if you were to start fresh, more like the MotherDuck story, right? So right now, would you take anything from your BigQuery story or experience and build it here, except for the easy query part?
One of the lessons was, optimizing for execution speed. If you have two databases, um, or two products at some date, sufficiently in the future, the one that ends up winning is going to be the one that is moving faster than the other one. Doesn't matter. It doesn't matter where they start. And I just had seen in BigQuery the way things got so slow. I mean, partly because, it was a problem of success. When you have some of the largest banks in the world and like there some of like really, really critical things are running on your technology, then you have to be very, very careful. Part of it was complexity. Part of it was, just the way the sort of bureaucracy at Google started to sort of gum up the gears and things took longer. And so, like, one of the lessons I took away was like, pick something that's going to let you move fast. And I think, we standardized on, or we built around DuckDB, which as an open source database was one that was moving extraordinarily quickly. And then just as you sort of build the company, make sure that you optimize for things that can allow you to keep moving quickly. Obviously, once you start getting customers and paying customers and people that are using it for critical things, like that does start to put a limit on, like, you don't want to just be in move fast and break shit mode for, when you are dealing with people's businesses. But you can also do things, and you can do things on parts of the product that do let you kind of continue to have the ability to make changes quickly, and you just need to make sure that you test well and have the right internal processes, et cetera.
Now, it's clear that there is this myth, and somebody should be benefiting from this myth, right? Who is that?
Well, it's the incumbents, for example. I remember a couple years ago, Snowflake and Databricks, they had like this kind of very public spat about benchmarks. And so Databricks said, hey, we're a data warehouse. We can run this data warehousing benchmark, and we're like twice as fast as Snowflake. And then Snowflake says, not so fast, you cheated. And then Databricks says, no, you cheated. You're you're a dirty cheater. Like, it felt a little bit juvenile the way there was this sort of back and forth. The thing that I noticed though is in the small print was the size data that they were using was like the TPCH 100 terabyte data set. And like from working at BigQuery with some of the largest customers in the world, nobody actually ran queries over data of that size. Like, they weren't like the benchmark scans that much. That's how much data is actually used, in the queries. Some people do have data of that size, but they tend to look at the, an individual partition, an individual chunk of it. It's just like, wow, like these two, giants are kind of duking it out, but they're kind of operating in this space where there's actually kind of nobody actually cares, or nobody, like, it shouldn't actually matter to anybody. But I think that they still do benefit in convincing people that this is the way systems should be built, and that they are important. And I think, it's just some of these things are, they the mentality dies hard, partly because, they do see, there are a handful of customers that do run at large scale, and they are kind of the most lucrative customers and the loudest customers. They're the ones that the product teams, the leadership teams are focusing on making these people happy. And so they're going to continue to make sure that they hit these like, giant data scale cases, and then they kind of leave everybody else um, in the lurch. And that's really what we solved MotherDuck to help like address the 99% of people who like kind of stuck with the with the use cases that the larger players didn't actually care about.
Basically, do not design for the corner case, right? Design for the 99%.
Which is like a great, like, just sort of is an engineering principle. Like, there's always the case where like we have like these two sets of customers. One has this really hard problem, and the other one doesn't. And you could say, well, and then the one set of customers that doesn't have the hard problem is much larger. You could say, I'm gonna design for this common case, and I'm gonna make the other one work. Or you could say, I'm going to design for this rare case, and because if we don't design around that, it's not going to work. It's not going to work well. As an engineer, I always like to focus on the common case and say, hey, we'll make this other thing work. Like, this is not actually the biggest, like, because if you design around that, then it's going to make you like do all kinds of ugly, gross
Exactly.
things that are going to pessimize what everybody else sees.
In fact, I would probably confess that I am the other side of that engineering. It probably gives us that kick. When you have a harder problem that's hard to solve, you're almost looking for problems that you could solve with passion, not really problems that really exist, right?
Right.
And you might do some extra effort to make sure that this problem is real. It's not like cheating or convincing others. It may be convincing yourself that these problems could be real, and it's going to get there. Yeah, I can completely see what you're saying.
Like, those corner cases are the more fun problems to
Exactly.
work on.
Exactly. Yeah. Now with the AI in play, right? Right now we have a lot of small queries going in from agents. Right? So that exactly is clearly the idea. That's the commonality. Does it change everything upside down?
I mean, absolutely. I think, just across the modern data stack, we've just had this. We've been in this stable equilibrium for a while, where you have your ingestion tools, you have your transformation tools, you have your analytics, your query engine, and then you have your BI tool. And I think that AI being, arriving on the scene, it is helping to sort of like eliminate the silos. And so to give an example, Claude is really good at, turning natural language into a SQL query and figuring out the SQL query to write, but then also building a visualization on top of it. And one of the things that we noticed quickly is like, hey, once we had an MCP server running and we could run these natural language queries, is that like the visualizations that Claude was building for us was better than our BI tool. And much more, easier to be like, well, how do I add error bars to this? If, you kind of try to click around in your BI tool to figure out how to, make a projection work or whatever, and exponential or log or whatever, like, it's just a pain. Versus in Claude, you just say like, add the projection and make it yellow and add some ducks to it. And like, and it would do that. And then, we're like, well, we don't need a BI tool anymore. We built something into the product that can sort of host the visualizations created by AI and allow you to share them and have them be up to date. So that's sort of the one side. The other side, there's data ingestion, and so you have Fivetran, that helps you get data from HubSpot into your data warehouse. Well, if you point Claude at HubSpot, give it the HubSpot documentation and say, get my data into Snowflake or BigQuery or whatever, Claude's going to figure out a way to do that. And so I think that AI is really dramatically changing the landscape, and I think everybody's going to have to adjust. I don't know what the resulting landscape is going to look like, and I think, but it makes it exciting. It makes it, I think, more exciting than things have been in the last few years, where it seems like, okay, we've sort of like, these are the players of the modern data stack. This is exactly how you do things. And you need to have all of these different tools in order to be successful. And now it's like, hey, well, like all you really need is, an LLM, your favorite LLM and a data warehouse. and then you can, and then anybody can be successful. And it's not just, not just the data team, but you can have, your salespeople and customer engineers be able to kind of pull things themselves. I think the other question is, what do agents mean? And so I think the next side of AI is sort of when, agents arrive on the scene. And I think agents are going to need a different type of engine. Like agents, a human is capable of sending X queries per hour. You have to write the query, you have to think about what's the next question you want to ask. You probably have to debug the query, and a computer and an agent can basically hammer the system because it can make decisions much faster. So the things it is going to want to do is it cares about latency. If your queries are taking 10 seconds and then it's taking 2 seconds or 200 milliseconds to decide the next question, then most of your time is spent on queries, not on decisions. And if you can cut that query time down to 100 milliseconds, you can get you know orders of magnitude more work done per unit time. And so I think that's one of the things where, like, BigQuery, we said latency doesn't matter because we're designing for throughput. Snowflake is also very similar. Is like they're designing for throughput, and latency is not very good. So I think a query engine that's designed for latency is useful. Also being able to let run lots of agents in parallel, to be able to actually branch off your state and have agents actually starting to, modifying things. So I think there's a bunch of different types of things you'd want out of your data system, if you're having agents that are in the driver's seat, versus a human. And like an example, that we use relatively frequently with one of our internal agents is like, you want to do a root cause analysis, like what's going on, being able to dig through the logs.
Yeah.
And and an agent can try a bunch of different parallel hypotheses, and multiple different agents can all be like, going down different threads. Was this it? And like they can put, and then they'll know that just doesn't look quite right, or they may end up deciding, hey, this is actually the needle in the haystack. So you can get a lot more done and a lot faster than a human. And for the query engine, it looks very, very different when you have that kind of access patterns versus humans, who are thoughtfully typing their queries.
I hear you. I hear you 100%. And I can see that happening almost everywhere too, right? So right now, the expectation from an agent is not a millisecond, probably not absolutely a 5-second response. It needs the data a lot faster than humans. So that is very clear. Now, agents, this is almost a very hot topic these days, right? I see people, in fact, that's a very common word that people would get a little shocker when I ask, what exactly is an agent? That's a very interesting question, because now I can call something that goes into my bank account, takes it money, spends it on my behalf on a stock that it's thinking it's going to go up, an agent. I can also call something that's going to create a report and send it to, probably flash it on to like 10 people, right? That is also an agent. Now, the autonomy on this agent versus the autonomy on this agent is very different. This is drastically different. You may not even need anything outside of an LLM here, but in this case, LLM is almost absolutely useless, right? Because you cannot take a decision based on any large language model, right? So how in your mind, right? Generally, this is not even a question about this topic, but how do you define an agent?
I think an agent is something that tries to simulate human decision making. Like an example that people don't think of as an agent, but absolutely is one, is you just go to ChatGPT, and when you type a prompt in ChatGPT, often what it'll do is it's going to try a bunch of things. So like it's not just like you give it a question and it returns you an answer. You give it a question and it goes off and like tries to research and investigate that question. And if it's doing analytics, and so if agents that are doing analytics, it'll do what a human would do. It'll like, you ask, tell me about, why did our storage revenue drop last week? So that's the kind of question that I often ask. And so it'll start, figure out where is storage revenue stored, and it'll start to poke at the schema, do the same thing that an analyst would do when they came up with a new, where confronted with a new system, what are the field names? What's in this uh, table? What is it? They would try. It looks like I could join it with this. Oh no, that didn't work. Oh, it looks like this table hasn't been updated since November. Like, most real data systems have some cruft in them, and a human can generally figure it out. And with a little bit of documentation, and you can obviously give agents the documentation in in the form of like a context layer, which is sort of the one of the other sort of hot topics that everybody's is talking about. But it's going to do a bunch of operations and eventually get to an answer. That's a simple agent. There are some agents that will kind of do the equivalent of that to answer a broader question, or they may just be running the same thing over and over again and, looking for changes in the output. I think if you have an agent that runs evals on your data and, is going to try to notify you or fix things or do something when something changes, when something's out of the ordinary, I think there's rich agents where, they have lots of power and probably an expensive LLM, and then there's poor agents which have a very simple task and may have a local model that they're operating. And I think still trying to figure out what are the right ways to solve problems with these things. And they all get things wrong sometimes, and so you need to also have feedback loops and mechanisms to handle it when they do get it wrong.
It's clear that big data is mostly a story and not a real problem. So now, what do big data engineers do?
I think that as I kind of was describing, like a lot of the stuff that analysts do can now anybody can do it, which I think is as people whose job is analytics, that's likely scary. I think from a humanity standpoint, the fact that somebody who's in marketing can now answer questions about what their campaigns or customers that they would have had to file a ticket and wait days to get those answers back. I think the fact that you can do that is a net value to them, and to sort of similarly on the data engineering side, if anybody can sort of pull the data from HubSpot that they need, what does it's not great for their expected job prospects, but it is great for being able to get more stuff done more quickly. I think though it's going to be sort of like, yes, I can walk into the kitchen and find something to eat, but also it doesn't mean that there's no value for chefs. And I think that yes, people are going to be able to get some of these answers themselves, but having somebody who actually is sort of building high quality dashboards, apps, reports that that are maintained and up to date, and when something breaks, they're gonna fix them. I think the need for somebody who can do that is not going to go away, because just like the marketer who can get questions answered about their campaigns, yes, they are going to be able to be successful, but when that breaks, or when the thing that they look at every day is not working, you kind of need somebody who can figure that out. And maybe you have 20 people answering similar things, and you want to standardize, and you want to sort of clean things up, and you want to say, hey, this is the right way to do it. And and then the ability of an agent or an LLM to make sense of data depends highly on the quality of the data model. If you also have an agent creating the data model, and that a bunch of you can end up with a mess. And so I think to some extent, I think engineers, data engineers, and analysts are going to be kind of making sense of kind of the mess that gets created when people get let loose on some of these systems. And probably and I think, yes, you're going to have people that they just have a question and they need it answered, and they go get that answer. But I think also somebody is going to need to, maintain these systems and the architecture around these systems. And so I do think that, the net result is going to be, I think the data engineer is going to be more valuable to an organization. You might not have as many, but I think that they are going to be extremely valuable, because the the ROI that, the value they can create is going to be, go from, hey, this is is a mess, to actually having things you can make like high quality decisions about.
Jordan, you solved one of the hardest problems in computing, right? So then, and BigQuery, as we all know, is a super popular product, and there are fans out there as well, right? And you've been doing that for decades, before you realize that, you know what, only a smaller segment really need this kind of complexity, right? Why did it take this long for you to realize?
So first of all, I don't think I solved one of the hardest problems in computing. I think I was part of something that helped people solve one of these problems. So I want to caveat that a little bit. I do think that it took a long time because the systems got pretty good. We were able to make it easy to sort of mask some of the flaws. And in order to build something, it's like when I started MotherDuck, one of the things I realized was if we were going to build it today, if we we're going to build BigQuery today, we would build it differently. And so, we kind of set out to say like, okay, well, how do we do that? And it takes a long time. It takes a lot of energy. It takes a lot of like really smart people banging their heads against problems, and in order to get it to the level where it's at least at parity of the incumbent, is really hard. And so, I think that was, that was one of the reasons. And I think that there's still the myth of big data. Um, and I don't know why it's been so persistent. I do think it's the assumption that, well, when it grows, I'm gonna need more. And I think it's just also people, their expectations, their intuition hasn't caught up with the actual state of technology. I think that's actually something that often happens when there is technological change, that the intuitions that people have around what works, what doesn't work, what's slow, what's fast, what's easy, what's hard, it takes a long time to catch up. And so when you think about like the machines being larger, networks being faster, laptops being more powerful, a bunch of things started to become possible that like weren't possible. There used to be these rules of thumb around, you know when when is it acceptable to have a page fault. And then generally cloud systems, they run without swap, because page faults are like horrendously slow. But with SSDs, page fault, is not so bad. And like, but people still have this like rule of thumb in their head that it's like, oh, page faults are terrible. And I think that there's a bunch of rules of thumb in how people think about systems and how people still design systems, that is still hasn't caught up to some of the changes. And I think actually the really, really interesting one that is forcing change very quickly is with LLMs. A lot of things that people just assume is going to be hard. It's going to be really hard to rebuild this UI. It's going to be really hard to like add this thing. And all of a sudden, you can just ask Claude, and Claude code, and it'll just do it. And so I think that is, one of the hardest things, just to sort of wrap your head around and develop an intuition around, okay, what can we get done, and what is, where are we gonna, and what can't we? Because there are also certain things where Claude Code still doesn't do a great job, and LLM still don't do a great job. And sort of then you need to rebuild your intuition around which things are those and which things aren't, that they aren't. And then it also changes every couple of weeks when the new model comes out. It's like, oh, well, now this thing that I thought was impossible now is like trivial. So, it's exciting times to be building.
And I'm assuming this is about engineers trying to future-proof things, assuming that there will be complexity in the future. And often it's a moot point, right? You never get there, or that complexity will never exist, but you still end up building for that complexity. And that hurts your common use cases. And that's the additional complexity. And that's exactly what you kept in mind when you started MotherDuck. Now, for the entrepreneurs, right? How do you enjoy the journey? How hard is it?
So first of all, I'm having a blast. It's a lot of fun. And um it's hard. I don't have kids, and so like, I'm going to use an analogy that I probably don't have a right to use, but I think from a difficulty perspective, it's like having kids, in that like it's hard, like, and things happen that you don't expect to happen and that you never thought you'd have to deal with. And there's things that it's like, I have to deal with this and this sucks. On the other hand, like, it's incredibly rewarding. It's incredibly, there are thrilling moments and there are wonderful times and there are, things that you can certainly be proud of. And it's a roller coaster that, sometimes even within a single day, it's like, this is amazing. And then, wow, like, this is brutal. And and then the next day it's something else. And so, like, if you're not in for a roller coaster, like, I would say don't do it. But I also think, like, it's fun. You get pushed um to what you can, what things that you thought you wouldn't be able to do, and you learn things that you thought you wouldn't be able to learn. And I think we're incredibly fortunate, and that, like, it's been working out well, and we're growing like crazy. And, like, so, like, we have so many tailwinds and so many things that are working out for us. And not everybody has that serendipity. But I also think, it gives you the opportunity to sort of, like, get good at recognizing, serendipity and opportunities when they come. And some you screw up and some you don't. And, like, and then you learn and you do it again.
Absolutely. Serendipity probably is the key to success when it comes to a startup. I agree with you. So first up, thank you so much for sharing the journey with us. Especially these open conversations do help people when it comes to making decisions, especially choosing the right tech, building with the right tech, and probably making the right choice in life too, right? So thank you so much.
No problem. Thanks so much for having me.